Now, we've done a lot of stuff that was Science 10. We've talked about work, we've talked about gravitational potential energy. I do want to take you away from Science 10 and introduce something new. And this is another type of potential energy. In Science 10, you pretty much focused exclusively on gravitational potential energy, but there's another kind of potential energy that you actually have a lot of familiarity with, but you might not think about it. So those of you, a lot of you have probably come across elastics in your lifetime and stretched them, played around with them. Then, as you stretched it, maybe you stretched it a little too far, elastic broke. Or maybe you stretched it a little bit, let go of it, and it snapped back and it kind of hurt you. Well, every time you stretch that elastic, you are storing energy in that elastic. So when you let it go and it snaps back, all that energy is being transformed into kinetic energy, and then that hits you, it's going to hurt a little bit. So anything that we can stretch or compress, that is also going to have potential energy due to its state or position as well. So if I take a spring or an elastic and I stretch it out, it's going to gain energy due to that stretching. We want to be able to calculate that energy, and this is what we refer to as elastic potential energy. So that is going to be energy stored in elastic objects, so things that are stretchy, or things that we can compress, like springs and strings and elastics, things like that. So elastic potential energy, it's going to be the energy that results from an object being altered from its standard shape. So kind of like if you were to leave it alone, and we don't want permanent deformation. What that means is, like, for example, with the elastic, if we stretch it out very little and let it go, it'll go back to its normal shape. If we pull on it hard enough and break it, we've deformed it, it will never go back to its original shape. Those of you that have played with slinkies as a kid, you'll know that if you stretch out a slinky long enough, it will get all twisted and it will not go back to its normal shape. So we're trying to stretch it without it being deforming. Now the issue that we're going to have here, though, is that the force is not going to be constant. Again, I always reference that elastic. You'll know the more that you pull on an elastic, you're going to feel it getting tighter and tighter, and it's going to be harder to stretch it apart. What that's telling you is that the force is not constant, because the farther you stretch that elastic material, the more force that's going to be required to stretch it, because that thing really wants to go back to its resting position. But we can use graphical analysis to kind of help us out with this again. So we have this graph here, we have this force position graph. We found to calculate the work, and we know work is just change in potential energy. This allows us to find the force on the object. This allows us to find the work, because we also know that the work is just equal to the area under this curve. Now, this is something we'll look at a little bit later, but for elastic materials, the force is going to be this K times X. So K is going to be this thing called the elastic constant. It's basically a measure of how stiff your object is. Higher K value, more stiff. And X is going to be that displacement from the equilibrium position. It's not how far it's stretched out, it's how far it's stretched out from its equilibrium. So like, for example, if I have, say, an elastic and it's resting at this position, and then I stretch it out to this position, the X value we're looking at is that distance from the equilibrium position. We're looking at this here. We're not looking at this total distance. So that's something to be aware of. Now, if we have a force position graph, we can find the work. So work is going to be half. The base is going to be our position, or X. And then the height is going to be the force, which I just have here as Kx. So I have half times X times Kx. This is actually going to give me 1/2 Kx squared. So with that, that is going to give us an equation for the elastic potential energy of an object. So again, we use this for things like springs or anything stretchy or elastic. So EP is going to be 1/2 Kx squared. So EP is our elastic potential energy in joules. K is the elastic or the spring constant in newtons per meter. And X is, again, that displacement from the equilibrium position. The only thing we have to watch out for is if we have to calculate the change in elastic potential energy, you have to be really careful with this squared term. So if I find this change, we have this 1/2 Kx2 squared minus 1/2 Kx1 squared. So we have this x2 squared minus this x1 squared. So you have two distinct terms here. It's very tempting to just say, oh, change in potential energy is 1/2 K, and then the change in x squared. This is not correct. The square makes this a little bit more complicated, so we have to do the full working out here. We can't just do the change in x and then square that. We have to do the x value at the final point squared minus the x value at the initial point squared. So be really careful with that. So this brings up another point. Can we have multiple potential energies in a problem? Yes, you can absolutely have gravitational potential energy and elastic potential energy. You can have both, you can have neither, you can have one or the other. The main thing when you're dealing with potential energy, you want to specify what type of potential energy is involved. And questions on exams, that will also be specified to you. We want to tell you what type of potential energy it is, or you have to be able to deduce from context what type of energy it is. So like if I lift up a box off the ground, that's a context clue that we're dealing with gravitational potential energy. We're not dealing with a spring. So just something to be aware of. All right, let's do a quick example on this. So we're told that the elastic constant for a spring, we're told it's 750 newtons per meter. So we want to find out how far we have to stretch this thing from its equilibrium position to store 45 joules of elastic potential energy. So we know that the potential energy is just going to be half kx squared. We would like to find x. So we know that 2EP, if I multiply it by the 2, is going to be half kx squared. And then we're going to divide both sides by k here. We're going to get this 2EP over k is equal to x squared. What that's going to tell us is that x is equal to the square root of 2EP over k. We know the potential energy, we know the spring constant, so this is going to allow us to find out how far from equilibrium we have to stretch this. And then we have the 750 newtons per meter. Big thing here, don't forget the square root. So we are going to have 90 divided by 750 square rooted. So we're going to get about 0.346 meters. So what this thing is saying is that if you want to stretch this material, if you want to have 45 joules of energy, you got to stretch it out by about 34.6 centimeters. Now, part 2 of this. Let's say we want to double the elastic potential energy stored in the spring. We want to find out how much farther we need to stretch it. So we're not looking by how far we have to stretch it. How much farther do we have to stretch it from this point? And that's kind of the trick on this one. So first of all, let's see how far from equilibrium we have to stretch this thing. So how far from equilibrium? So again, we have this EP equals half kx squared. And then we know that x is just this 2EP over k. Well, this time we'd like to double the potential energy. So in the previous part, it was 45 joules. So this time we'd like the potential energy to be 90 joules. So we get 2 times 90 joules divided by 750 newtons per meter. So this time we are going to have, let's see here, wrong number. So I'm going to have about 0.490 meters. So this is telling us how far from equilibrium we have to stretch this to get 90 joules. So to get 90 joules, this has to be stretched about 49 centimeters. But we want to know how much farther we have to stretch it from the previous example. So if we've already stretched it 34.6 centimeters, how much more do we have to stretch it to get to this point? So to get how much farther? So we're just going to say, we'll call it this x2 minus x1. So we've already stretched at 0.490, so we need to stretch at 0.490 meters. We've already stretched at 0.346 meters. So what am I going to get here? Let me punch this in the calculator. So I'm going to get about 0.143 meters. Now you might say, hang on, Mr. O'Donnell, 0.490 minus 0.346 is 0.144. Correct. I'm using the extra digits in my calculator. So like 0.144 is what you get if you kind of round it early. This is using my unrounded values. But if you put 0.144, you would get full marks for that. Like that is perfectly fine. But I just want you to know that's why I'm getting that 0.143. Right, the last little piece here. So we want to sketch a plot of EP versus X. How could we plot these to get a straight line? Well, we know that EP is equal to half kx squared. So if I look at this, so if I plot EP as a function of x, well, that x squared is telling me we have a quadratic. So what I should have is I should have a parabola, or a parabolic shape. So as x starts to increase, EP is going to really go up quite quickly. So this is going to be our quadratic function. There is a special way we could plot this and get a straight line. What we would do instead though, and this is something that you're going to do more of in Physics 30, but we're just kind of introducing it right now. I still want to plot EP, but instead of plotting EP versus x, I'm going to actually plot it as EP as a function of x squared. So instead of having x on my axis, here I'm going to have x squared. If I plot EP as a function of x squared, this will give me a straight line. And let's look at this. So I got EP equals 1/2 kx squared. Well, if I plotted EP on my y-axis and I plotted x squared on my x-axis, that's telling me that this piece left over, because we know a straight line is y equals mx plus b, that's telling me that this slope of this line is just going to be half of my spring constant. Or if I was interested in finding the spring constant, I could say it's twice the slope. But like I said, this is something we work on a little bit in Physics 20 to introduce it in Physics 30. We go way more in depth in Physics 30. And we'll see a little bit more of this later, but just to kind of bring your attention to it.